Hello again, welcome to week 4, which is dedicated to functions in OCaml. So in this week we will start with functional expressions. We will see that in fact you can write down expressions which denote functions as a value. As it turns out, functions are what is called first-class values in OCaml, which means they have precisely the same status as any other value that you can write down in OCaml. Then we will continue with functions with multiple arguments and related to that, so-called partial function application. And finally, we will look at some applications of higher order functions applied on lists, and we will look at mapping functions over lists and folding functions over lists. So the syntax for a functional expression uses a new keyword which is called function to denote that we are defining a function. So it's function, then some identifier, arrow, an expression. So what does it mean? This rule construction is an expression which denotes a function without a name. This function takes one argument called id, and it has a body which is written in the expression exp. And of course, in general, you would use the identifier id as the parameter of the function when writing this body exp. An example of this would be the function which maps x to x plus 1. This would be written function x arrow x plus 1. So this is quite simple to write down. Of course, the scope of the parameter of this function would be restricted to the expression as it was before when we defined functions having a certain name. As any expression, a functional expression also has a type. And now, since we are defining a function, this expression, of course, has a functional type. So the type that we would obtain for this construction would be some arrow type t1 to t2, which is a derived type. t1 would be the type of the parameter id, and t2 would be the type of the expression, which is the body of this function. So let's have a look at some examples of functional expressions, which are expressions which calculate a value of functional type. Like here on the first line, we have the expression which calculates the successor function, that is a function of type int to int, and it sends x to x plus 1. We might of course have more complicated expressions and the body of the function, like here on the next line. This is the function which sends a y to a list of lists which uses the y in its definition. So we obtain here an expression which has the type int is sent to int list list, that is a list of integer lists. Finally, we have here a new thing about function application. What we see on this line is that, well, what we write at the place of a function when we have a function application is in fact not necessarily a name of a function, but it can be any expression which gives us something of type function, like this functional expression written on this line, and it works perfectly fine and returns what we might expect. Now, using these functional expressions, we can now write down a different way of defining functions using a name. In fact, the form that I showed to you in week 1, where we defined a function f by writing let fx equals e, is just an abbreviation. It's an abbreviation for the definition of an identifier f, which means that something which we could write as let f equals something, and the something is the value which will be assigned to the name f, which is a function. To summarize, this means that the form let fx equals e is just an abbreviation for writing let f equals function x gives e. So we just have one unique form of defining an identifier, which is let name equals something. The only thing which is more general than what we have seen in week 1 is that the something, the expression, is now an expression of a more complicated type, that is a functional type. Here we can now see that in fact we have used so far just something which is an abbreviation for the binding of an identifier to a function expression in the definition of a function. So this is the first form that we have seen to define a function in week number 1. So here we define a double function in the usual form, and we write let double x equals its body, and we see that this in fact defines a function which is called double, which behaves as expected. Now, as I have explained to you on the previous slide, This is just an abbreviation to bind the identifier double to a functional expression which denotes the same function. So we obtain exactly the same response from the top level, and in fact the function that we have obtained calculates precisely the same thing. The most general form of a function definition or of a function expression is in fact the following one. It always starts with the keyword function, and then in general we have a sequence of pattern matches. So we have a sequence of patterns, and associated to each of these patterns we have an expression, and as always with pattern matching, in the expression we can use the identifiers introduced by the according pattern. You might note that the form which I've shown to you at the beginning of the sequence, function x arrow exp, is just a special case of this general form where we only have one case and the only pattern is reduced to only one identifier. You might note that in this case we don't have a vertical bar in front of the pattern, which is allowed in the syntax since the vertical bar in front only of the first pattern is in fact optional and it's not mandatory to write it. Now let's have a look at some function definitions using pattern matching. Here we have, for instance, the length function on lists, and observe that in this definition we use directly after the keyword function a distinction of cases by pattern matching, and we don't have to introduce a name for the formal parameter of this function. So when we pass this to the top level, we obtain in fact a function of the expected type AlphaList to int, and we can, for instance, evaluate this function on a small example and convince ourselves that it works. A little bit more interesting is to do the same on tagged data structures as we have seen them in week 3. So here we have, for instance, a small data type of expressions which are either integer constants or which are composed using a binary addition constructor. Okay, and now we can define a recursive function which evaluates such an expression using pattern matching and using the form of a function definition without an explicit parameter. And you might observe that in fact the form how we have written this function mirrors more or less precisely the definition of the type on which we are working. So we obtain here a function of type expression to integer, and now we can evaluate our function on a small expression, and if you do the calculation yourself in your head, you will see that the result is precisely what it should be.